Okay, hello everyone. Another session, and today we discuss OSPF basics. I think this is after we discussed basics of routing. I think we did static routing, and today we start with dynamic routing, where we discuss protocols that are involved in finding routes in a network. And the main one for our ACIA is OSPF. We do have a number of protocols, but OSPF, I think, is the one that will probably the sole focus of ACIA. So static routes are manually configured. If a network topology changes, static routes have to be manually adjusted, which restricts the large-scale application of the routes on a live network. So basically, not I think, static routes work perfectly fine on small networks because they're very easy to configure. But for larger networks, they're not very easy to scale. If you have a large network, you have a large number of routes, it's very difficult to configure a large number of routes statically. So in terms of scalability, that's an issue. They are not that much flexible. That's the reason why we have dynamic routing protocols. A protocol basically works if you configure a protocol, exchange of messages between my routers, letting each other know the routes are not manually but automatically. So in terms of scalability, in terms of flexibility, obviously my dynamic routing protocols, they have that upper hand when we are talking large networks. So that's why we will be doing OSPF basically, which is a dynamic routing protocol. Objectives of this one, we are going to describe advantages in classification of the protocols, describe OSPF concepts, describe the working mechanism, and the last objective, we are not going to be doing that one. I think that one will come a little bit later, probably after one or two more sessions. I'll be expecting everyone to have installed ENSP. It's a bit tricky to install that one, but I think after we've installed ENSP, that is probably where we'll be able to start with configurations. So for now, I think we'll just be focusing on defining what OSPF is, what characterizes OSPF, and how does it work basically. Why dynamic routing protocols? I think I've already touched on this one. The reason why is static routes, they're very difficult to scale. I think that's one of the main reasons why we have dynamic protocols. With static routes, and my links connecting my network 100, it probably will mean I'll need to configure close to 100 static routes. That's very difficult. With dynamic protocols, they will do most of the work on their own. Routes will be um, automatically updated without you needing to reconfigure them. In this case, we have static routes being unable to dynamically respond to network changes. So in the diagram, an example, we can have a static route configured right here, where it says if I want to get to R2, how do I get there? That's a static route. But what happens if this link fails? From perspective R1, routing table yedu inenge route iri ndorinenge riripo. Routing inoshandisa information iri routing table. Saka link iri rikadhakwa, even if there is another passage yekusvika ku R2, which is this one, it will probably not be installed in routing table if we have manually configured this one. Unless you had a floating route, it now means you had two routes configured. That's work already. Unless you had that, it means you probably never be able to access networks on R2. But in a case where you have my dynamic protocols, dynamic protocols can dynamically learn kuti we have a link fault, therefore we need to change our route. It can change on its own without needing some backup routers and stuff like that. I think that's an easy explanation of basically why we need to have my dynamic routing protocols, especially if we are talking large networks. Classification, I think we touched on this briefly. Classification of protocols can either be by ASs, which is an autonomous system, or can be defined by their working mechanism and algorithms. By AS, what do we mean? An AS is basically a collection of networks which are operated by a single service provider. That's what an AS is. And when we define dynamic routing protocols by ASs, we have what we call IGPs and EGPs. And for IGPs, this is basically one ISP. Everything is under one ISP. For EGPs, these are multiple ISPs. So if I'm trying to connect between ISPs, the type of protocols that I use are these ones. If I'm connecting within an ISP, the type of protocols I use are these ones. Then we have by working mechanism, we have distance vector, we have link state routing protocols. Distance vector showing us the distance, basically how far in the direction, which is the vector part, how far and in what direction is a route. That is what distance vector routing protocol shows us. A little different with link state. This one shows us the routes. Where are the routes? This one. With link state routing protocols, these ones, we have a case where we have each router building a topology basically. So in this one, we have a router, every router in the network building up a topology of the whole network. Then from there, a route is chosen from that map. This one, it shares the routes directly. If you want to get from A to B, this is how you go from A to B. You go this far, you go this distance. What link state routing protocol does, if you want to go from A to B, it will tell you this road, characteristics of that road. How big is it? How congested is it? How easy is it to travel? That's what we call a link state. We can say a link status. So this one, it shares link statuses. What's the status of the link? That is what it shares. This one, it shares routes directly. That's the difference between my dynamic vector routing protocols and my link state. I think probably as we go and as we try to explain what OSPF is, we'll better understand what link state protocols are and how do they differentiate, how do they differ from distance vector routing protocols. Okay, and there we have a distance vector routing protocol. A router running a distance vector routing protocol periodically floods routes. Through route exchange, each route learns routes from neighboring routers and stores the routers in the routing table. So basically with this one, what you have is where and how far and in which direction is a route. So you can see from here, which direction through R2, where if I want to get to that network, 3.3.3.3, that is what distance vector routing protocol shows you. In what direction am I going through R2, where to this network? It basically advertises routes. That is what defines a distance vector routing protocol. On another hand, link state routing protocols, they flood LSAs with distance You could see here, there were routes which were being flooded. But with this one, we have what we call link state advertisements. In link state advertisements, uh, basically describes a router's interface status information such as the cost of the interface and a connected interface name. So that is what is being shared, not the routes. It shares the cost, most importantly, the cost. What's the importance of knowing the cost? The cost, we can directly link it to this thing, the bandwidth. If the bandwidth, we have a lot of bandwidth on a link, it means the cost will be low. It means probably, definitely that will be a preferred route over the other one, which with a higher cost. So instead of flooding routes, we flood link statuses. From the link statuses, that's where we can then choose which route is the best. And with that, I think we can move to the next slide so that Tifambe, we have a lot of slides on this one. Right, LSDB creation. I think Taktopinda, the function of OSPF, basically OSPF starting with LSA flooding. LSA flooding is more of a way of updating, updating our routes, basically. Then, if we update our routes, all the LSAs they are stored in what we call an LSDP, link state database. So every router has a link state database, and it gets updates via link state advertisements. So every time a link state advertisement is being flooded to a router, it is being stored here. What does that mean? At the end, the LSDB contains the description of the entire network topology. Because my LSAs, they're updating about the link statuses of every router. It means at the end, if all the databases are synchronized, this one will be the same as this one, will be the same as this one, will be the same as this one. And what this LSDB will contain is all the statuses that are here. And when we say all routers in the same OSPF area have the same LSDB and they all contain the same topology, they all know the same topology of the network. That is what we mean. Because this LSDB will contain the cost here, the cost here, the cost here, the cost here. That is basically the map of the whole network. So from my LSAs, which are my updates, if we flood my LSAs, they are synchronized in my LSDBs. If database read is fully synchronized, then every router in the network in the OSPF area knows kuti topology yes yakaita sei. Every path, every route, it now knows kuti yakaita sei. From there, we have an algorithm which performs the SPF calculation, the shortest path first. I think this is where the OSPF name comes from, definitely. So now we have LSDB fully synchronized. Takuziva every route, every link in the network, every status yainayo. What's the interface? What's the cost? That is part of what defines the link status. Takuziva zvese. Now we calculate, if I want to go to network X, which route, considering my link status is the best one to get to that network. Algorithm and it calculates the shortest path first. Can I calculate that path? That is the path which will be installed in the routing table. So it's a bit different than distance vector. Distance vector, we flood my routes. We choose with route renade and the RIP, considering administrative distance. What's the other one? Considering other metrics like anacost, that is how my distance vector routing protocols work. This one, a bit different. Dynamic routing protocol. My statuses, they are updated, synchronized via my LSDBs. Then from there, an algorithm is run. That algorithm will choose the best path at any given time, and it installs it in the routing table. I think this is the part after the SPF algorithm has done its job. Based on the SPF calculation results, each router installs routes into the routing table. So in summary, how link state protocols work. Number one, we have neighbor relationships. This is where we establish relationships between my routers. We'll discuss later on exchange of what we call my yellow packets. My routers, they exchange my yellow packets so that as Zvani. During exchange of my yellow packets, this one and again, in every router and again a router ID. That's where they exchange my router IDs. Kuti vazivane, kuti my routers azivane in short. So that's the first step in my link state protocols. Kana my routers azivana, they now have a relationship. From there, they can now exchange my LSAs. They exchange my LSAs so that my LSDPs are synchronized. They exchange my LSAs kuti my databases are synchronized. Because kana azivana from this step, rinenge rine database raro, but at times my database iwawo anenge akasiyana. Patinoenda pastep iyi, kana madatabase akasiyana, they will need to be synchronized so that they all be the same. How it is done, my LSAs, they are flooded. And DOM updates actually, my LSAs, they are flooded. Then, kana asynchronized, takwenda pa step number 3. Kana ASA asynchronized, takwenda pa step number 3, where we have the SPF calculation. SPF calculation kanaitwa, takwenda pa routing table. The base route is installed in the routing table. Iwo ukachienda unoti show IP route, display of ACIA. How do we see the routing table ACIA? I'm forgetting. CCNS show IP route. Ukachienda uona the routing table yako. That's where you get to see a route which was chosen after a summary of all these steps. It seems we're already in OSPF, but introduction to OSPF. It means base up we're just discussing link state protocols. That's the basic function, how link state protocols function basically. That's the summary. Now, OSPF is an example of a link state protocol. We have OSPF version 2, which is for IPv4 networks. We have OSP version 6.3, which is for IPv6 networks. OSPF routers exchange link status information. Very important, but not routes. Link state information is key to perform topology and route calculation. OSPF collect link status information. Each router uses SPF algorithm. OSPF supports VLSM. Multi-area design enables OSPF to support a larger network. I think we'll touch on multi-areas pamberi pichana. But basically, this is an introduction which gels perfectly with the summary link state protocols at either. There we have an example of a campus network probably going to use to run OSPF to implement reachable routes. As we can see, I think this is a single area OSPF, or the routers are in a single area. Therefore, they will have the same LSDB when synchronized. I don't think there is much here. Not sure the idea behind this diagram, but it basically shows us a campus network, probably all routers in a single area, meaning they will share the same LSDB when synchronized. Basic concepts, area, OSPF area. I think I've already defined this one. An area is basically What defines an area? The area is considered as a logical group, and each group is identified by an area ID. Right, we have what we call area 0, which forms what we call the backbone. This is the backbone of the network. So if we are using single areas, if we are using single area, then it is area 0. If you're using one area, that's a single area. It cannot be anything but area 0. Area 0 forms the backbone of the network. If you are going to have multiple areas, it means probably you have another area here. We can call it area 1. We have another area here. We can call it area 2. The idea behind my areas is so that we don't have a lot of processing within uh, a given area. So I'll give an example. If route area munomu tikaita 1,000 routers, what it means is 1,000 routers are ASI. They will have to be synchronized. Panosendwa LSAs, 1,000 times LSAs will be sent to every other router. ASA or synchronized so that they have the same LSDP. That's a lot of processing. Panoitwa flooding ema LSAs. That is a lot. So you can separate. It's sort of the same concepts. Zine segmentation ema networks. Going back from ana subnetting, VLANs as well. It's segmenting a network. So you can have 300 here, 300 in this area, 300 in this area. It means you have reduced processing in every area. My LSDP arufana ofanana in 300 muno, 300 muno, 300 muno instead of 1,000. Then can now connect my networks are or my border routers, which basically connects all these networks. Tonight my ABR, my border routers. In this course though, we won't be focusing much on multi-area OSPFs. But it is important to understand the idea behind having a single area and having multiple areas. So for smaller networks, manageable networks, we can just have area 0, which is a single area. But if we are going to have larger networks, it will be recommended you have multiple areas so that you don't put a lot of processing on my routers in a given area. I think that's the concept and idea around my areas. Then we have my router IDs, which basically identifies a router in an OSPF area. We have an IP address, which identifies a host in a network. We have a router ID, which identifies a router in an OSPF area. Two different things. So because they are both identifiers. So every router in an OSPF area, it has a router ID. This router ID can be manually configured. You can manually configure this. Router ID is 1.1.1.1. Or you can choose to use a loopback interface on that router. Why loopback interface? Because that's an interface which is always up. Or you can use a physical interface on a route. So if you don't have a manually configured ID, then any loopback interface, it should be the highest configured loopback interface will automatically become the route ID. If you don't have a loopback interface configured, definitely on a router you have one of the physical interfaces configured. Then that will become the route ID. What is it's important? You're going to realize that Pamberi, we're going to talk of elections, choice of DRs and BDRs. That election will make use of these IDs as well. Is that true? We'll see if it's true. Cost value. OSPF uses cost as route matrix. Each OSPF enabled interface maintains a cost value. Default cost is 100 megabytes over interface bandwidth. Right. We have a metric here, cost. Every link, it has a cost. You are seeing it has a formula which is used to calculate that cost. That formula is, we have what we call the reference bandwidth over interface bandwidth. So this interface bandwidth is fixed for any given interface. If you have a fast Ethernet interface, its bandwidth is 100 megabytes per second. If you have a Giga Ethernet interface, its bandwidth is 1 gigabyte per second. However, reference bandwidth E, we can play around with it. It can be configured. It can be changed. It's just a reference. By default, its value is 100 megabytes. So if you want to calculate cost, for example, by default, cost your fast Ethernet, it will be 100 megabytes over 100 megabytes. If you want to calculate cost a Giga Ethernet, it will be 0.1 100 megabytes over 1 gigabyte per second. However, cost values edu my integers 1, 2, 3, 4 zvichienda zvakadaro. So this one, if we are using this default reference, will not be valid. So reference here can be changed. In an example where you have both my Giga Ethernet and my fast Ethernet, you can change reference yako probably to the highest interface yaunayo. So if I change reference yangu to 1 gigabyte per second, then cost yangu will be 1 gigabyte over interface bandwidth. That means for fast Ethernet, it's no longer 1, it's now equals to 10. 1 gigabyte over 100 megabytes. For Giga Ethernet, it will now be 1. Chine cost shoma, ndo chine high bandwidth, ndo chiri more preferred in terms of my matrix. So here we have a concept here, cost value, how you calculate it, how we can change the reference bandwidth. This one we can change it. Pama configurations, the reference bandwidth, we can change it to fit whatever interfaces we have. Here you could see serial interface 0. What's the cost if we're using the default reference? 100 over 1.55, 1.544. It will give you a cost of 64. And basically, I think that is how we define cost. That is how it's calculated. That is also how it can be manipulated by changing the reference bandwidth. Each OSPF interface has a specific cost because of the particular bandwidth value. In the routing table, the cost of the OSPF route is 7510 plus 1 plus 64. All right, this is also important. Cost, year link, it's cumulative, if that's the right word. So for example, cost, if we're on R3 here, the cost yekuti network ish will be cost per link ir plus cost per link ir plus cost per link ir. That's the total cost. So cost is accumulative. It adds up until we get to the destination network, basically. OSPF package types. In OSPF, we have my packets which are exchanged. We have what we call the hello packet, which is periodically sent to discover and maintain relationships. So hello packet is basically used to establish my relationships between two routers. If I have two more routers, kana chida kuti azivane, iro rinosenda hello, iro roresponda rosenda rimwe hello. Zvakureva kuti marouters edu akuzivana. Hello packet, most importantly, contains the router ID, which identifies a router. We have what we call the DD packet, database description. It describes the summary of the local LSDB, which is used to synchronize the LSDBs. Kana tazivana, this one we share is this database description. Database description is basically its LSDB before synchronization. This one will also share its database description, LSDB before synchronization. Then pachaitwa comparison ye LSDB iri nere parouter panapa, iri nere parouter panapa. Ndo panoonekwa kunzi what's missing. That's where synchronization starts. Kana pane anything chiri missing, we have another packet which is called the link state request. Requests a needed LSA from a neighbor. LSRs are sent only after DD packets have been successfully exchanged. Kana ta exchange ama DD packets edu, if there is information missing, we compare my database edu. If there is anything missing, we send a request. That's another type of a packet. Kana request rasendwa update away, what we call an LSU. An LSU is basically a sum of LSAs. That is what defines an LSU. My LSAs akawanda is what's defined in a link state update. So kana taisa request, then my LSAs anova avatanga flag. My LSAs anouya over synchronizer this database. Then we have another packet, link state acknowledgement, link state ACK, which basically acknowledges the receipt of an LSA. So if I can go a bit further, my LSAs kanauya anosvika kunofila information yangaisipa. Then if all information has been filled, it means my LSDBs edu are synchronized. Then iri rekunokwira nerekunokwira anobva afanana. Kana afanana, we are fully synchronized. SPF calculations take off. Three types of OSPF entries. We have what we call the neighbor table. Patinotanga establish my relationships. That's where we have the neighbor table. These two routers, 1 and 2, aka exchange my hello packets, akuzivana. Ndikauya panapa ndikati ndida kuona the neighbor table using this command. Neighbor table inondodza kuti R1 ineighbor yedu. That's a type of an OSPF entry number 1. The neighbor table, which is displayed by a router after successful neighbor relationship. After a successful neighbor relationship. In this example, we have these two routers defined by those router IDs. Ndikauya display my OSPF P angu panapa. I can see ndiri pana router 1. Neighbors, Giga Ethernet 100 neighbors is this one. It's a neighbor because we have successfully negotiated a relationship via this address basically. But I think the most important part, ndeyekuti tine neighbor ish. Kana ndiri pana R1, inondudza kuti neighbor yangu ndi ish. That is what the neighbor table is. Neighbor table, OSPF neighbor relationships are established by exchanging hello packets After successfully exchanging those packets, that's when you can see neighbor app. If you don't successfully negotiate, then you won't be able to see that. So that's what defines the neighbor table. Neighbor table, it comes from database, runs adjacency database. Probably it will come in the end, this information. Adjacency database. Yellow packets, adjacency database, neighbor table. LSDB table. So with this one, it lists information about all the routers in the network. All the routers in the network. The 188 neighbor table, it lists just your neighbor. This one, it lists all the routers in the network. Why it lists all the routers in the network? Because what an LSDB database contains, the link state database, what does this contain? It contains the topology of the whole network. So I connect topology network ESA. It means if I display my LSDB, what will I see? I will see the topology of the whole network. In this case, no network AD. My network's AD. Okay, it's showing my routers add on a network iripo-ish, network irapai. We have only one network iripo. So the LSDB, it gives me information of all the routers in the network. My routers add to one. Dai akawanda ese aifanira kubuda pa-link state database. The type of fields, let me see, LSDB stores LSAs generated by a router itself and received from neighbors. The type of fields indicates LSA type. Run the display OSPF LSDB to query the LSDB. In short, LSDB displays information about all routers in the network. I can see my time in Ingea found up. Use the same link. We have another session.